LC3, as I'll come to at the end, is really composed of exactly the same materials and, undergoes the same kind of hydration mechanisms we have in all cements. And this gives us great confidence in its long-term use. It's not a totally different material. It's an evolution of a material we've been using for 200 years now. So we start at a simple level because, this hydration process is really fascinating because it's behind the whole reason why we can start with something that's fluid, we can mold it into different forms, and then it becomes hard. So at the beginning, we really have a concrete, and in the concrete we have stones, and then we also have what's called cement paste. And at the beginning, this cement paste is like these gray grains of cement floating around in water. And that's why you can put it in place and make different forms out of it. Now, what you don't know is the chemical processes that are going on, which you can't see. But in essence, these chemical processes are, first of all, a dissolution. So that's like, if you put sugar in your coffee or your tea, it dissolves. That's the first step. But what's really interesting about cement is then the different elements that go into the solution, into the water, can start to form new compounds which precipitate. And that's what I've drawn here in red. This is what we call the hydrates, and they have a larger volume than the original cement grains, and therefore they fill in the space between the cement grains, and they start the whole thing together. So in this way, we go from a fluid suspension to a hard solid. We still have some pores left over, some of these holes, and of course we want to minimize the amount of holes, because if we minimize the amount of pores, we maximize the strength, we maximize the durability. So that's a schematic diagram. If we come to the real thing, we can sort of see how this is happening by taking images in the scanning electron microscope. So you see here, these are cement grains. You take a bag of cement, we impregnate it in resin, and then we polish it. And you can see these cement grains are actually quite complicated. They contain several different phases. And, we have names for these phases. It kind of goes back to when people didn't really know what the chemistry was. So the thing that there's most of, they called alite, A for alite. The thing next most common, abundant stuff is called belite. And these are actually, now we know, these are impure, what's called C3S. And I should remind the non-specialists here that when we write C in this cement chemistry, that C actually stands for calcium oxide. And the S stands for silicon dioxide. So this is tricalcium silicate. And this is dicalcium silicate. And these two phases, these are actually solid during the high temperature process. But the other two phases make a liquid, and that liquid enables you to form these clinker nodules. And then when you cool it, these phases form from the liquid. And these are called aluminate and ferrite. So that's what the cement looks like before you start. And then you add water, you have this hydration process. And if we now look at a micrograph of a hardened cement paste, this is what we see. So these bright areas here, these are the cement grains that haven't yet reacted. We don't ever get a reaction degree of 100%. We almost always have some unreacted cement left over. And in fact, it's quite interesting. You can see, for example, one of these bigger grains, that we can actually see where the original outline was. That was the original outline I'm tracing here. And during the hydration process, this depth of the grain has been replaced by hydrates. But more importantly, there are a lot of hydrates you see in the other space, and that's what's holding everything together. So you've basically got two kind of areas you can distinguish. You've got this lighter gray area, which is what's called calcium hydroxide. And then you've got this kind of darker gray area. And this is mainly what's called CSH, or calcium silicate hydrate, but it's also containing lots of other phases. And as I said, the important thing is that we really understand what all these phases are. We know their structure. Now, as I showed you in the first schematic, this whole hydration process takes place in the solution, in the water. So first of all these things here dissolve, and they form all these different ions in solution, and then these ions precipitate to form these phases. This is the kind of volume repetition of the phases in a hardened cement paste. You can see about half of it is this phase that's called CSH, about 15% is calcium hydroxide, etc. And because everything goes through solution, we can actually use thermodynamics, and we can use phase diagrams to very well predict what phases will form. And that's also a very powerful tool I'm going to come back to later on when we talk about blended cements, because this shows that the phases that form are the thermodynamically stable phases. So we can, we know what's going to happen. Thermodynamics is a very basic aspect of physics and chemistry. So that's what's going to form. The other thing, of course, we're interested is what is the rate at which it forms. And usually we follow that by looking at the heat output. So as things react, they tend to get warm. If you actually put some cement in a plastic bag and add water to it and mix it between your fingers, you will be able to feel it sort of heating up. And it's heating up because of the reactions going on. Now, we can measure that in a fairly sensitive instrument called a calorimeter, and this is the kind of output we get. We see this initial, rapid evolution of heat as the cement phases start to dissolve. That's what happened to you, isn't it? What do I have to do? Okay, we're back. And then we have a period of slower heat evolution. This is often called the induction period. And from a practical point of view, this is extremely important because this means you have the time, you make your concrete in a ready mix plant, you then have like 2 or 3 hours to transport it to the job site and put it in the forms. And we also have a very well elaborated admixture technology, which means you can prolong this period. If you have some bad traffic, you can prolong this period to make sure that your cement doesn't set too early. But then once you've got it in the forms, the reaction starts to take off again. You have what's called this acceleration and the deceleration. Now, from a scientific point of view, the two questions that people have looked at for the past, getting on for 100 years, is this question, why do we have this initial slowdown? And the second question is, why then do we have this limitation here? Because you see already after one day, the rate of reaction has become quite slow. And that's actually a little bit of a disadvantage because it means that one day we have maybe quarter of the final strength and we have to wait another month or so to get the kind of design strength that we're aiming at. So there's been a lot of work to understand the mechanisms that are going on here, and I'm going to talk about that briefly, focusing on 3 periods. First of all, the induction period here, then this main reaction, which is where about 50% of the reaction takes place, and then what happens in the longer term. So for many people, it seemed to be a bit of a mystery why this reaction starts off quite strongly and then slows down. And there were many, many hypotheses put forward. People thought, well, we must be forming some kind of layer on the surface, and that layer must be slowing down the reaction. Well, it seems a plausible theory. I'm not going to go into all the details, but basically I'm going to tell you that's completely wrong. And, we know it's wrong for many reasons. One reason is that, when these hypotheses were put forward, then we didn't have very sophisticated tools to look into the microstructure. Now we do. And when we look into the microstructure in the SEM, you can see this is a cement grain here. You've got these products forming on the surface, but you see most of the surface has not got any products on. There's no evidence of any layer. And, you've got these kind of big pits here. This is where the cement grain's been attacked. And the resolution here is quite high. That's 100 nanometers. Nanometer is 1,000th of a micron, so it's a millionth of a millimeter. So it's very, very small scale. And now, there's been a lot of work going on what's called geochemistry. Geochemistry is all about the formation of rocks. And I'm not going to go into all the details, but they really had a little bit the same problem, that most minerals you find in the earth tend to dissolve quite quickly and then it slows down. And we can see that here is the regime of fast dissolution, and then we have a slowdown. And so we want to, and this has been studied in great detail, and what's understood is that in the fast dissolution regime, you have a lot of energy available, and that energy means you can create a lot of these etch pits. And that's not cement, that's actually quartz. So this has been done on a lot of other minerals. And then as you come closer, as more ions build up in solution, you have a slower dissolution, and you can often see these kind of steps here. Because a step moving on the surface, it's like, if you're trying to move a carpet, if you try to move the whole carpet at once, it's really difficult. But if you put a kind of kink in the carpet and then move that kink along, then it's very easy. And we did some work with a very brilliant student I had called Patrick Giant. He worked on this a few years ago, and basically fabricated this material we call alite, showed that when you dipped it in pure water, you had etch pits very similar to what you see on quartz here. And when you dipped it in lime solution, then you don't see these etch pits. And he looked at the theory from geochemistry, transposed it to cement, and you see exactly the same form of curve as in the previous case. And then another group working in Dijon did these experimental measurements, and you can see these experimental measurements really fit very, very well with the theory. So we now have a very consistent theory which says there's nothing particularly magical about this slowdown. It's very common. It happens for a lot of different minerals. And, we know everything that's behind it is to do with energetics. And this sequence we could take in a atomic force microscope. We actually took these pictures underwater. If I play them again, you can see this sort of nice sequence. First of all, we form this rough area, which is like the fast dissolution. And then as the hydration is going on, you can start to see these steps forming here. We get this transition into the step retreat. So now we really have a very good understanding of this period. We really realize that this protective layer idea, even though you read it still in most textbooks, this is really wrong and it cannot explain many results. And instead we have this very coherent theory coming from geochemistry, which really has a sound theoretical basis. We get an excellent agreement between theory, experiment, and modeling, and we can explain all the experimental observations. So then we started working on the main hydration peak, and this was actually the subject of Shashank's PhD. And this was really challenging because if we look at this peak, I don't know why this won't move now. Okay, so now we're looking at this period here, and here we want to answer this question, well, why do we get this slowdown? Well, we know what's happening in this period. This is the period when we get the main growth of this CSH, this calcium silicate hydrate phase. And this calcium silicate hydrate phase has this rather interesting morphology. It's often been described as like a sea urchin or something like that. You see, we have these kind of needles that grow out from the surface. And, here's now a transmission electron microscope. This is now being tilted in the transmission electron microscope. And you can see these kind of needle structures there. They're actually made up of kind of foils. So as we rotate it, you see the foils run along the needles, and across the needles, we've got this kind of system with a lot of holes in. Now, people have worked on this question for a long time, and, it's kind of basic way of doing science. You sort of make a hypothesis, you make a model on the hypothesis, and then you see if they agree. But, this doesn't always mean you're right. And, one of the PhD students we had just before Shashank, or I think it was at the same time, Mercedes Costoya, she did the experimental work. She generated a very nice set of experimental data. And since she did this work, then there's like 5 different mechanisms, all different hypotheses, which all claim the hypothesis is right because they fit to the Costoya data. Well, that's obviously impossible because, they can't all be right. And the 2 most common hypotheses in this period are, one, we could have diffusion through some kind of layer, or the second, that we could have impingement of the product. Well, that's the kind of theories, they're coming from metallurgy and things like that. And actually, the problem was we found out that neither of these are supported by the experimental evidence. So the idea of diffusion through a layer is, this is your cement grain here, and you start to form CSH, and the idea is that's a kind of homogeneous layer, and the reacting things have got to go through that layer. So here you see the solid lines. This is the experimental data of Costoya, and the dots are the modeling that was done by Shashank, and it looks great. It looks like, well, this is the answer. But that shows you the danger, because if you took all these different particle sizes, this number here is the particle size, then to make this data fit, you have to have quite different values for the diffusion coefficient. And that's actually a complete nonsense, because the product you're forming in every case is exactly the same, so it should have the same properties. So it's just a coincidence that you can make these graphs fit. It doesn't actually mean that's the right mechanism. And since then, we accumulated lots of other evidence from other students which really negate that hypothesis. Here we see this CSH. You can see how kind of holy it is. It's quite easy for things to go through this layer. And in fact, we form this big gap behind the layer. So this is the cement grain, and here we've got this gap. And, here's another picture where we can see these CSH needles, and you can see there's a bloom great hole. So it's not actually a continuous layer at all. And then we could do the same thing with the impingement model. This was actually a hypothesis put forward by somebody called Avrami for solidifying metals. He worked on this hypothesis in the 1930s. And the idea is that you form a first little bit of solid, and then the rate of growth of that solid is proportional to the surface area. So as they first start to grow, the rate of reaction goes up. And then as they start to impinge on each other, the surface available for growth goes down. And you get these kind of curves. And these kind of curves look like the cement hydration curve. So, naturally people said, oh, well, this explains the slowdown. And you can get fitting, but in fact you find that the parameters you have to use are really random. And this kind of shape of curve is quite simple to model by mathematics. You only actually need two different parameters. So, you've got to really understand what's happening in terms of physics and chemistry. And we realized that, one reason this couldn't be the explanation is because if you increase the water-cement ratio, you put more water in. If you put more water in, then the cement grains are further apart. You would expect a very big increase in the amount of hydration before the slowdown, and you don't see that. And then we had this, and then we could kind of, model what was happening to these needles. Had another student who measured these needles very carefully in the SEM. And what she found was that these were growing very fast at the beginning, and then the growth rate was slowing down. And most interesting was to look at the impact of very small levels of zinc. So this is A-light, just normal A-light. And this is A-light containing just 3% zinc. And you can see the dramatic effect that has. In fact, it slows down the reaction at the beginning. But once the reaction starts, you see it goes much, much further. You get 2 or 3 times as much reaction in the main hydration peak. And you can see in terms of strength that at 28 days, both of these have just about the same strength, but at 1 day, you've got about 3 times the strength. So this seems really great. If you could apply this in real cement, then you could speed up your reaction by 3 times. Unfortunately, it doesn't work as well as that, because of various things I'm not going to go into. But in this fundamental case, you can also see the big impact of the zinc on this CSH. So these are these needles, and you can see this is the reference case here, and this is the case with zinc here, and you can see that the needles, they become much longer and much thicker. So then we could come up with a new hypothesis. We could put this hypothesis in a model, but again, here I want to emphasize here that we took all the parameters in our model from the experiment. We had no fitting, and we could get very good fits across a whole range of different experiments. So, of course, we don't really know everything. We still have some open questions. For example, why should the growth be fast at the beginning and then slow down? Is it to do with the solution concentrations? Is it to do with these complex foils and how they form? We don't know everything yet, but we've got the basic idea that we need to look at, because we looked at this wide range of variables and used different models, our hypothesis that fits all the facts at the minute is we get this fast growth of needles to a critical length, and then their growth slows down. So after the peak, well, we've still got a lot going on because, as I said, when the reaction slows down, we're just at 1 day, and we need to wait another sort of 28 days or so to get the 30% more hydration, but that gives us 70% extra properties. So it's very important, this ongoing reaction. And again, what's happening there? Well, we did several theses on this. We did look at a number of parameters. And then when we plot this data, now this is cumulative data. So most of these curves I've been showing you at the earlier are what's called differential curves. So that's the rate of heat evolution. If we integrate this, if we add up all the heat under this curve, we come with this cumulative curve here. And this cumulative curve, we can see all these bunch of different experiments. The first part in the beginning, that's the main hydration peak I showed you. When we integrate that, we get this line here with an inflection point about here. At long ages, then we see everything seems to be fairly similar again. And in the middle, we've got a lot of different things happening. And basically, we could see that this difference in the middle was somehow related to the space available. Now, that's, as I say, somehow, because there's a lot of complexity after that. But again, what we could show is that a lot of other hypotheses that have been proposed do not work. For example, a lot of people then said, well, this is again this diffusion barrier. And that seems quite possible because, now the layer is much, much thicker. So it seems this could be a barrier to diffusion. But if that was true, that would mean that as you had more reaction, you would have a thicker layer. So the reaction should be slower. And that's, again, not what we see. If you take these two curves and this simply change the water-cement ratio here, at this point on this curve, we have a higher degree of reaction, so we should have a thicker layer. But you can see by the slope of the curve that the rate of reaction is higher than in this second case there. Okay, so it's kind of to do with space, but that's more complex. And that's more complex because, in fact, what we find out is a lot of these pores are not filled with water. And if you think back to the beginning, we need the solution there. We need the water there for the reactions to take place. And then at the second level, the pores actually become too small. So actually, if we look back at this picture here, you think, oh, there's a lot of space here for all these hydrates to go in. But in fact, these big spaces, you can see what kind of dimension they are. They're like several microns across. And in fact, we can work out the size of the pores that still contain water because there's this very fundamental curve which comes from physics, which is called the Kelvin-Laplace equation, which gives you the relationship between the pores that still contain water, solution and the relative humidity. And we can actually measure what's the relative humidity in a cement paste. And these are the kind of measurements we get. This is Portland cement, this is LC3, this is LC3 at a lower water cement ratio. And you see the relative humidity is going down. It's about 85% in this case of the LC3. And then we apply the Kelvin-Laplace equation, and we calculate that at 85% relative humidity, only pores bigger than 10 nanometers still contain solution. 10 nanometers, you can't see that on this kind of scale. This is 10 micrometers. A nanometer is 1,000 times smaller than a micrometer. So you see none of the pores that you see in this SEM image actually contain water. It's happening at a much finer scale. And, the details I'm not going to go into. We haven't worked out all the details yet. It's very complex because the crystals are growing and not rounded, so a lot of things are a little bit difficult to understand. But basically, by looking at how the pore structure evolves in the very long term, we can actually sort of differentiate between pores that still contain water, and they're filling in quite fast with hydrates. The other pores, I said they didn't contain water. Well, that's actually not completely true because they do retain a thin film of water on the surface. And it seems we can see by this shift in this line here that we will get a very slow growth in that film on the surface. So we now kind of fairly well understand this long-term process, that we have an upper limit by the fact that a lot of the big pores become more or less empty except for this film of water. And at the lower limit, the pores become really small. The hydrates can't go into it. I don't know why it cuts out on me. Anyway, so that's the hydration process for Portland cement. And as I said, it's important because we really understand that very well now. So now we want to know, well, what happens when we put all these blended things in, when we put in what we call supplementary cementitious materials. And it's important to understand, and this comes from the basic chemistry of the earth, that all these different additions we make, whether they're fly ash or whether they're slag or whether they're calcined clay, there's a lot of similarities in their basic chemistry. So this, is in this phase diagram between calcium oxide alumina and silicon dioxide. This is the Portland cement here. You see slag is very similar, and that's why we can use a lot of slag as a substitute. Fly ash is a bit further away. That's why it's not so reactive. Calcined clay is actually quite different because these two, slag and fly ash, are kind of glassy phases that just react on the surface, whereas calcined clay's got this layer structure, which is what makes it very reactive. And, we can look at the phases, we can overlay that, we can work out what are the phases that are going to form. And it actually becomes very interesting because we've got this big phase diagram with all these complicated phases there. But we really realize that the only little region we need to be worried about is actually this little pink triangle here, because we need calcium hydroxide to help the reaction of these additions like calcined clay, like slag. And once we get up to this line here, we've run out of calcium hydroxide, so they won't really react very much. So we just need to know what's in this little pink triangle. And we know that because, again, everything's going through solution, like I told you before, except we've got slightly more things over here. We haven't just got the clinker phases, we've got the SCMs. But the idea is the same. And thermodynamics has been really very successful in modeling what phases. So we published this back in 2011. This is looking at the reactions with silica fume. Silica fume, because it's very simple. You're just adding silicon, and you see as you add more and more silica fume, you start to react the portlandite, the calcium hydroxide, and then the other phases change. And then at this point here, you've run out of things to react with the silica fume. And after that point, the silica fume just stays there unreactive. And you can do the same for fly ash. You can see, again, this is starting to consume the calcium hydroxide, and then the fly ash just doesn't react anymore. And we did this thesis where we took these different blended systems and we compared, what does the thermodynamic simulation give compared to a mass balance calculation and compared to experiment. And there are some discrepancies which we can understand, but basically the agreement between all these methods is really quite good. What is changing, and what's quite important, is we see quite a shift in the composition of the CSH. So, this is looking at the calcium to silicon ratio of the CSH, and this is the ratio in Portland cement. And then you see when we add slag, it actually shifts quite early on to a lower level. And we can measure how much alumina is contained, and we can work out that a lot of the alumina in these systems will go into the CSH. And we can look at the CSH over a wider range, and you see all these additions, slag, fly ash, silica fume, and also calcined clay, but I haven't got the data here in this graph, show this kind of shift in CSH composition. Now, this shift in CSH composition, people often say, well, does this make a difference to the strength? Well, the answer is no, because this change in CSH composition is occurring at the atomic scale, and the strength of CSH is determined by the kind of, friction between those kind of needles I showed you earlier. So this is very well understood. And then the other effect of SEMs is obviously on the reaction rate. And, we have two things. We have, first of all, what we often call what's called a filler effect. So the impact of these fine supplementary cementitious materials on the reaction of the cement, and then the slow ongoing reaction of the stuff itself. I'm not going to talk about that because I haven't got enough time, but I'm just going to talk about the filler effect here and understanding that filler effect, because it's quite important, because during the first day or so, most SCMs do not react. Calcined clay actually reacts a little bit, but it's still the basic clinker, the Portland cement part, that dominates the reaction. And even then, the SCMs have an effect on that clinker reaction. So we could study this by looking at comparison between a material containing slag up here and a material containing fine quartz. So the quartz was chosen to have the same particle size as the slag. And you can see then when we normalize, we have to normalize this heat flow according to the clinker content. So obviously if you put in 40% slag, you have a lower heat evolution overall, but relative to the fact there's 60% cement in that, you can see this reaction is actually a bit higher. And the quartz and the slag have more or less the same effect. Here we can see from about 30 hours or so, then the slag one starts to have a higher heat, and that's actually the heat of the slag itself reacting. So we took some time to really look at what was happening. A lot of people said, well, you've got extra surface, and extra surface gives more surface for your calcium silicate hydrate to form on. And that seems to be the case, because here in the SEM, these are the quartz grains, and these are the cement grains. And you see in both cases, we see these little bits of CSH forming on the surface. And then that CSH forming on the surface, you see in both cases, seems to grow. So that seems again to be a plausible hypothesis. But then again, when we try to see if it works out quantitatively, we see it doesn't work, because you increase the surface by 2 times, you only increase the amount of reaction by 20%. So there's got to be something else going on there. And in fact, what's going on is the physical effect of the grains rubbing together, and these little bits of hydrate, they get redistributed. So you actually have the same in a cement mortar when you have sand grains there. And we could see that everything has a similar effect depending on the shear between the particles, although in fact the limestone, and this is where limestone and calcined clay becomes important, because fine limestone has a particularly beneficial effect, that really does stimulate the nucleation of this CSH. So now with limestone, you can see there's a big difference between the cement grains. This limestone grain has lots more little nuclei of the CSH, and that means limestone is particularly effective, even though it's not reacting itself. It's reacting a little bit, but even apart from the reaction, it stimulates the reaction of the clinker. And that's why, it's really beneficial to have additions of limestone. Not too much, but, up to about 10-15%. So that's basically the filler effect here. And you see, if you put in a very, very fine material like silica fume, you can get a very big enhancement of the reaction. This is not the silica fume itself reacting. This is just the fact that the fine silica fume particles are stimulating the reaction of the clinker. And because of this, you have to be quite careful on readjusting your sulfate. Thomas is going to talk about that after me. So the final thing, of course, we want to come to LC3. And this is where we really exploit this synergy between the limestone and alumina. So first of all, we realize that limestone does react a little bit to form these carboaluminate phases. That was actually the thesis of Thomas back 20 years ago, I think he told me, who underlined that. And some people like Clarty de Wet showed that this could, be synergetic. You could have reactions between fly ash and limestone. But it's much more interesting when you have a rapidly available source of alumina, such as you have from metakaolin or calcined clays. And we can see that. So we have the calcined kaolitic clay. It's a pozzolanic material. So first of all, the silicate part goes into the calcium silicate hydrate. Also, some of the alumina goes into the calcium silicate hydrate, as I showed you before, but more of the alumina reacts with this calcium carbonate, which is limestone, and forms these carboaluminate hydrates. And we can see these carboaluminate hydrates. It's these peaks here. You see in OPC we have some of those phases, not very much, but in LC3 we get a lot more. And this was the first work we did with Mattia Antony. We actually did this in 2008. It was published in 2012. And we could see that, if you just added limestone, at low additions, this is 5% limestone. You see, it's really not too bad. At 28 days, the strength is about the same, but you add more limestone and, you add more limestone somewhere over there. But anyway, you have the two together, you get this beneficial effect. You get this higher strengths at 28 days. And that was the work that led us to this understanding that we have this synergy between lime and alumina, and that can enable us to go to very high levels of substitution and get very good performance, even with only 50% clinker. And, this is then the evolution of all the phases. As I'm saying, we can understand all these phases. They all agree with the thermodynamic models I showed you before. And, therefore, we can really have confidence. We've got nothing new. We've just got the same phases, but forming in different amounts. We understand the stability of these phases. We understand what's going to happen to them in the long term. So I hope you don't get too lost in all the technical detail. And I'd like to thank you